So now we should record. So Ferenc, thanks again for joining us. And now the screen's yours.
Yes, okay. Thank you very much. And thank you for the nice introduction. Yes, I will show you our activity, how we are developing a materials database. It's called HADB or hard coating alloy database. It's a material property database, and you see in the first slide so that it is a particular project because I have a lot of industrial partners and we are working together with them to achieve it. So of course I'm not doing it alone, so I have colleagues, and I hope it will work. Yes, you see here. So you see the team of the HADB developers. In the first line, you see the more senior persons, so they're providing the industrial contact, or you see also myself here in the list, and you see also Ricard Armiento. I want to emphasize him because he's providing the high throughput toolkit type of framework which we based on all our activities. So as a Python type of infrastructure. In the second line, you see the persons, they are doing the calculations and doing the stuff. First, Davide, who is an expert in doing AMD simulations for fracture. So this is where we are learning the mechanical properties. Suligosh was a postdoc with us that recently has left and moved to another group. So she developed a very nice CSV workflow for us, a high-throughput workflow to get data for our database. Santiago is a new PhD student working on Fourier diagrams to capture corrosion. Lalit, a PhD student who is doing AI and take care of the neural network, which is built into the database you will see later on. Similarly, Jonathan is a PhD student working on that AI part and the infrastructure, so to how to back up the database and communicate with the supercomputing center. Sure. So what is our outlook? What is our goal with HADB? So it is like establishing a digital infrastructure with a close collaboration with industry. Yeah. So what you see here on the slide is really a future step in a way. So a stack of a huge database on the left-hand side. I see first stack to represent something like the manufacturing part of manufacturing a material, so in the processes or the workflow data which you gather through the manufacturing. Here, the figure shows simply a deposition chamber which is used in all of these companies, how you actually make a thin film of a coating or a hard material or a very corrosive material, so resistant material. So input parameters like what is the gas inflow, what pressure, what type of current goes into the chamber to initiate the arc deposition. So there are lots of parameters what you can actually book here at that level. And then, of course, all these stuff what you measuring in a chamber should be somehow related to a sensor. So, and the sensor characteristic should be also bookkeep. So, and choose a proper sensor for your manufacturing point or your physical boundary condition. So it is very important stuff there. And then on the bottom is the database. What I will talk about mostly, it's a materials database where you have all material properties. And all this information in our sense goes into a data lake. And this is a concept where you can actually communicate with industry. This is how we are working together with hard coating industry, Sandvik, Coromant, or the nuclear industry, Westinghouse, or some others. I think it's a German company to let's say to provide coating for bone implants. So here is Westinghouse is developing a lot of cladding materials, how you could keep the nuclear fuels in the reactor in a very corrosive environment, or in case of Sandvik, where the metal cutting is happening, that is a high temperature situation where you have a significant load, so you need really stable materials there. All these companies, they don't want to actually communicate with each other, so they want to be independent. So that's why we offer this data lake concept, where they can take any type of data from us or any other open database, put it in the data lake, and develop your own kind of network, kind of product. So in that sense, we actually keep the confidentiality in a very high level. Yes. So, and then you can ask the question, okay, why do we need actually another database if there are so many databases on the market? So here in this slide, you can see most of them. It's probably an old slide, so because not all the databases are shown here are, but you see the major ones like Alexandria, Materials Project, Nomad, and ICSD. So AFLOW also I mentioned here. So you can ask the question, why do we need another database for that one? And that actually summarizes our challenge or our outlook in a scientific or closely industrial type of question. So first of all, we would like to go beyond the computational curiosity in a way. So I know that this is a little strong wording. So I used to say to my students that we should think as if we are in a lab. So it's not like just calculating and exploring the Mendeleev table of elements and putting all together. 0 Kelvin. So no, our industry or our partners are looking for more properties. So that's why. So what always we say, so industrially relevant materials are always should be multifunctional, should be multi-component also. So how actually you can tune the thermal stability, the corrosion resistance, and so forth of the materials in different directions. Most of the cases, they are metastable phases. So you should use a particular technique in the lab to deposit them, the thin-film deposit. And a very trivial example probably is the gum metals, which are where you have Ellenberg and Inver effects together. So these metals are also very close very close into an instability point, and that makes everything challenging from a computational point of view. Of course, we have the non-zero Kelvin situation because the real world is working there. And then we have thermodynamics and also mechanical properties. So we want to see how materials are performing in reality. That means also that we need microstructure and some type of multi-scale look on the material. A very interesting and old example to underline this, the importance of this one is shown here in the figure. So let's assume that you have your 0 Kelvin materials exploration framework to find some good piezoelectric material, and then you discover some morphotropic phase boundary in this type of alloy. This happened long ago, and then you see that 2 phases, the hexagonal and the Wurtzite phase, are actually competing energetically with each other. So again, I refer to the vicinity, and that will result in something extraordinary. And that's in this case is a giant piezoelectric response. But then you go into the lab, and then you deposit it with some magnetron scattering. So you ask your colleagues, so come on, do this deposition. And then you characterize it with TAM, let's say, and then you will see such a situation. So relative high temperature deposition at this concentration, very close to what was investigated here. So you will see a TAM image like that. So on the substrate, you will have some hexagonal phase, and you will have also the cubic phase. And then if you put it into a piezoelectric force microscopy, you will not see any piezoelectric response. And that's because what you are actually growing, what you get out has meaning only if you can actually consider also the multi-phase. So you have hexagonal cubic phase, the competing phases should be included, and also that was that at particular temperature and with the boundary condition. So that's the physical challenge or background or outlook. We have also another outlook in developing a database is more related to the infrastructure. So we would like to support the digitalized industry. The industry is digitalized, but it's more on the higher level. So we would like to have an open database with a certain confidentiality. That's always under discussion with different industries. So we say that we keep the data away from public usage for a certain period, or we are not allowed to pull it into data lake to use it in another context. We want to have a modular database structure to allow easy expansion on the initial level. And that was the point that we would like to have higher level stacks. Remember my original figure where we had this several stacks. So we encourage industry to borrow and take our database and implement own in-house data without sharing that even, or later on in case sharing that. So we also want to support data lake concept in a way, and we are working on it to allow different, a very diverse data formats like numbers, arrays, functions, figures, and so forth. And a very important point also is that we always wanted to have a very easy to use, easy to train, built-in machine learning model to predict material predict properties. Okay. So what is our freedom? What we are dealing with in the database? So we have an inhomogeneous data, so manufacturing process experimental data. We have, from physical point of view, we have external load, we have corrosion, we have oxidation, temperature. We also deal with, so we include in the database that one, so it's relevant for us. Because now, if I come to the different industries I mentioned at the very beginning. So, for example, methyl cut are relevant at 900 Kelvin, or if you come to the cladding materials in a reactor, so in a boiling water reactor, so they will be around 400 Kelvin or even above. So the pressure from higher temperature in the water, so it's a very corrosive environment what you see here. Or you have a case where you have a body implant, what you want to have for medical usage. Here you would like to have a material or a coating with stable and good performing at 300 Kelvin. Good performing means in this case is that should be actually the strength or the Young's modulus of the material should be very close to the bone, not to break your own bone because of the implant. And then we have the multi-component feature. So we wanted to have alloys, we wanted to engineer all these properties together. So we see the case that the competing phases will occur. I mentioned already this piezoelectric case where the cubic and the hexagonal phase are competing here. Similarly, I show it how the phase diagram in the background, so it changes how the binodal and the binodal lines are changing if you just consider the cubic phase or the hexagonal phase. Or if you have a multi-component alloy, you will know that at higher temperature age hardening, binodal decomposition happens, so it is included, or the mechanical investigation. So these are the points which I would like to emphasize. So what are the tools which we are doing or using? So we are using atomistic models. So we are generating a lot of SQSs. Even in HADB, we have inbuilt SQSs. So predefined ones which you can use, and also we are using in the CGT, in the machine learning model. So what mostly we are doing thermodynamical calculations, either with simply the bimodal, so we calculate elasticity, and then on that one we are using some quasi-harmonic type of model to predict thermal expansion. Or in case of unharmonic material, so I mentioned already the vicinity of instability. So a very unharmonic case, which is occurring in nitride, a major block of material we are focusing on. So we use the stochastic temperature-dependent effective potential method to sample the materials at a different temperature, or in case we would like to speed up more, so we develop some machine learning interatomic potential. At the moment, most of the cases we are using the MCP-based setup. Then we calculate elasticity for the alloys, and then here I just want to mention that we calculate the average elastic constant. So it means that even if we have an alloy, we are aware of the fact that in the case of an SQS, where you have an alloy, you break the symmetry, and then you need some averaging technique to get the right elastic constant. And then we also implement our MD, ab initio MD calculations, where we are actually using big supercells of the alloys, and then we do some tensile or shear type of deformation to check the strength of the material. To see, and then that we do it like stringing such a tetragonal type of supercells. But we also implemented and use some notch models to see plasticity and also plasticity into plasticity dislocation, inflation, and so forth. So these are the methods what we are using. And how the database looks like now, it looks like you can achieve the database on that web address. We have at the moment 300 entries containing many different chemical elements. So we have DFT calculations, we have ab initio MD entries, and then we have machine learning entries. So that's the welcome page of our database, HADB. You see the three main features here on the top. So that's searching for a certain alloy. We have a property map here. You can actually check the correlation between different properties, which is stored in the SQLite format. On top of the elastic constant, we are bookkeeping the mixing enthalpy, strength curve, and a lot of other properties, of course. And the third part is indeed the machine learning predictors using the CGCNN model and using data from materials projects. So, but in the later slides, you will understand how we are doing that. And then the header page also shows you where we have the elements, where we have the nitrides, which we are focusing on, where they're taken. So we have these transition methods and any kind of combination. Most of the cases we have also cut some carbide. Also. Most of the cases we have B1, B4, and B3 phases because these are the most relevant competing phases for our industrial partners. And here I already mentioned the nitrides. The nitrides are forming a group of materials where you can have a lot of metastable phases, and that's the point why we are taking that one here. The multifunctionality is a very important point, but also occurs many dynamically unstable phases. What we need to take care. So to get the elastic constant for such alloys, and particularly in a group of materials where you can have calculations. Now I translate the dynamically unstable phase to calculations where the material doesn't exist, or the calculation, whatever DFT engine you are using, will not converge. You need a very sophisticated high throughput workflow, and that's presented here, where we have 6 major steps to filter out all the candidates where we don't want to do calculations because it will take so much time. So, during this development of this workflow, we have faced with many issues how to can reduce the cost, the computational cost. So, just an info. So, if I take a cubic binary alloy for a certain concentration, let's say that you take this 50-50 titanium aluminum nitride already shown up. So one needs around 250,000 core hours in a HPC computer to get the elastic constant calculated. This is too much. This is too much. And then in case if you want to have it for several concentrations, if you want to have it close to dynamical instability, the elastic constant can be engineered very nicely, then you can forget about this type of workflow. You need to make some changes, and this is what we suggest here. So we suggested two major steps to consider. One is that one can start with really a low accuracy, unrelaxed calculation. That means that we take low accuracy. If you talk about watch, so then we really reduce the number of plane dates, and then we take really a small K-max in the blue and so on to get a feeling about how much time do we need to convert the computational time I'm talking about, or how much, or if it will even convert or not. And after that, so if it gets converted, let's say in a certain time, then we we have the equilibrium volume, and at that point we actually can do a relaxed calculation. So then we allow the atoms to move and relax, find the position. So and here we do a filtering, then we allow only a certain time limit and certain main displacement. If it goes beyond a certain displacement, then we say that we don't focus on this alloy further in the workflow. If the alloy, a certain alloy which we have selected, passes this stage already, then it can go into the situation that we calculate the relaxed and the complete elastic and so forth for that composition. Yeah. So here you can see an example so that you get a better feeling about what's going on. So let's say we took a B1 alloy. So it's a sodium chloride structure. Alloy, we created the SQS superset, and then we set up the concentration 0.5. So, and the first step, we generated 110, let's say, candidates. Then we did the low accuracy unrelaxed calculation. Only 100 have passed the converts. 10 of these candidates are not converting. And then comes the next step where we actually do the relaxation, and then we take those ones where you have a certain selected displacement inside the atomic relaxation. So you see that the biggest drop actually happens here. So when you be actually saying that, okay, yes, here you see almost a half of it actually has two big relaxations, and we throw them away, and only 36 at the end will go into the final stage to get the elastic constant. If you take a V3 structure, which is more open type, so then you see it's much drastic how it is changing. So how the atomic relaxations are bigger, and how many candidates we actually throwing away. So that underlines how serious is here the computational issue what we need to face here. So in that sense, in summary, so we started with the 110 alloys for the B1 structure at this concentration, and then the 146 in the B3 structure at this concentration, and then you will see the big difference, how many elastic constants can we actually store in our database. So it is really a huge drastic thing. So one needs to have a really clever workflow. That's what I want to emphasize here. And then if you come to the elastic constant, yeah, we are happy with those ones. Let's say what we can actually manage and calculate. So here you can see the calculated values. I just wanted to show up simply the different alloys. If you see any magnetic cases like the cobalt, so then you should see that it's non-magnetic calculation. So we calculate elastic constant. All these constants are the average elastic constants for the B1 structures and also the B3 structures. What you see already also here, I emphasized the previous slide, so that the B3 structures are much more severe in terms of computational cost. You need to run longer time, and then you need to relax them more properly. It is reflected also here that the difference between the relaxed and unrelaxed calculated elastic constant, because that's what we also do at the end, it can be actually more significant. So the difference is shown here on the red on the right hand side. So in some cases, in the shear modulus, it can go to 20% difference. So what we are saying at the end, so that for the B1 structures, if you compare these numbers, the differences between the relaxed and unrelaxed elastic constant. But the B3 cases, so we say that in case of B1 structures, one can get a reasonably accurate database without atomic relaxation. Meanwhile, for B3, it is not the case. The error is much higher. And that already gives us an outlook, a very important outlook that tells us that in case we would have, we would consider Bird-sized hexagonal cases or even more complicated, less symmetric cases, then the workflow development should be much more severe. Now, okay, but I assume that now we got an impression about the significance of the workflow, how the data goes into the database, and then we can see a little bit what is in the database. So you can, in the database, if you go to the search option, as I mentioned before, you can actually get a list of materials. You can filter them by temperature, method, and symmetry. So you see temperature, method, and method I mentioned already, the Ebony MD, DFT, or MLIQ you can get for the different temperature cases. Symmetry, that will be the B1, B4, B3, BK structures. Which is, I mean, here is the 25 is the B1 structure you also see here. For this case, it was not before. Yes, and then when you click on one, for example, here the niobium aluminum, then you will see what was the supercell, what we have used. You get some instructions, info how what the calculation is done, what the kind of extinction potential was used to be later consistent in materials project or with other databases. And then you can get also, you can download some files if you would like to reproduce the results, and then you get the elastic properties. On top of the elastic properties, you also get a visualization of the elastic properties. So you get a two-dimensional representation of the Young's modulus, let's say, or the shear modulus, and also the Poisson ratio. So in 2D and also in 3D. So if you, I mean, in case of niobium aluminum nitride, we got the almost a very nice spherical anisotropic model, which is shown here, or mostly on the circular behavior of the different moduli. You take another alloy, then you will have more anisotropic, what is represented here. Okay. Leaving the elasticity, we can go towards the ab initio MD data what we are storing here. So then we can assume that okay, we have a supercell. We take actually a long elongated superstructure. So it is like a pillar in the code, repeated pillars. So again, you get what we are doing here is that we are taking the structures and then we are pulling them along the Z direction, or we are healing accordingly of what we would like to know. Again, we store all the input informations, and then also we store some of the outcards which are clean, that they won't be so big, and then the stress strain curves also. These are also represented in a different direction. So here you see for this particular case, I think that was here is the alloy, so you can see this was a carbide, hafnium tantalum, titanium, zirconium carbide stress strain curve along the 110 direction. So it will look like that. So if you take the shear string curve in the 001 plane along the 110 direction in gigapascal, then you will see the signal. That's it. Later on, we have realized that so this is very ideal case. So and then we started to develop a new stress strain curve methodology. So where we have an ability MD simulation with a notch model, so which is summarized here. So we are building in some type of notches, and then we open this crack to see what's going on and how the stress strain curve is changing. So that gives more realistic data for material scientists and nuclear. And then we will keep all the extracted informations in the database, like third order elastic constants or the different strength values. The strength is actually just the maximum of this stress strain curve. Right. And yes. And then in case of you click on a particular case where we did a maximum and intermittent potential study at different temperatures. Then again, here you have a titanium iodine zirconium alloy. So the difference with respect to the other ones is that you have you can download the intermittent potential, what we have developed, and you also can download the training set. So in that sense, you can derive your own MLIF and then cross-validate our results. And based on the book kit or the store data, we again analyze the elasticity. The other feature is if you go beyond the search, then you have a customized property map, what you can check in the database. So it's built in, so it always shows all the data what we are having at the database, and you can check the different correlations. So here you in the X and Y axis, you can select the in-build quantities, but also you have a custom value, so you can divide them and check in your wish. Or if we also present the person type correlation matrix or R matrix. So this is a matrix which shows a perfect negative correlation with -1 and the perfect correlation with +1, blue and red. Here you can see. So you can see that the valence electron concentration is how strongly it's correlating with let's say the Poisson ratio or the Cauchy pressure or so forth. Or on the opposite way, we can see how the valence electron concentration is negatively correlated with G over B, so the shear modulus versus the bulk modulus ratio. So that gives really a lot of new information for industry to select the other material. Yes, good. And then we are coming to the third point in these small headers is the role of the built-in machine predictor. So where I mentioned we did want to have an easy model or descriptor and an easy training for material property. So the question is, so what happens if you type in a search for an alloy which is not existing in a database? So at the moment you have nothing, of course. You see, so I typed in titanium aluminum vanadium nitride, nothing is happening there. Or what happens if you are looking for a particular concentration which is not stored? Of course, we cannot generate SQSs for arbitrary concentration. So here I just emphasize that you have only particular ones. But when you, for example, would like to know the thermal expansion of an alloy, and it's I want to engineer, so you would like to see a set of continuous map. That is the point where the machine predictor is serving us. And what we are using the CGCNN or the cryptograph convolutional neural network approach, which is actually two layers of neural network. So first, you take a crystal structure, and this crystal structure is coded into a vector, a descriptor vector with the help of some convolutional layers, and that's explained here in this slide. I think some of you might be familiar with this, but I did a short intro. So if, for example, you take the first neighbor cutoff distance only to build a local environment, then you have such a octahedra. along each FCC lattice points here, and then you can build such a graph. So each atom or each position will actually form a node, and in between the nodes you will have actually edges or the distances or binding will happen, the first order binding. Both features actually will be stored in somehow and represented in a vector. So I think the nodal information is simply just related to the chemical element. So hydrogen would be the 1, 0, 0, 0, 0 vector. The helium will be the 0, 1, 0, 0, 0 vector. Meanwhile, the distances will be stored with the help of severally moved Gaussian functions and sampling the Gaussian distributions according to the distances in your crystal. So, and then if you have the U and V vectors, then you can convolute it in a long way. So with the help of this expression. So you see that, I mean, this is an advanced convolution because it's not just, I mean, the features are not just like the on-site node feature plus, I mean, orthogonal plus the distance, but also you include some neighboring nodal feature. Anyway, so if you do it, you can actually code this a very complex crystal into a vector. And then that's what you can see here. So you actually in each layers you have a different vectors depending on the size, and how many sides you have depending on the cutoff radii, what you are actually using, which is a hyperparameter. And then you pull together with a simple sum function into one single crystal representing feature vector. And then again, you use some simple neural network with some hidden layers, number of hidden layers. That again, a hyperparameter here, you can actually train the DFT value. And the DFT value can be here, bulk modulus, sphere modulus, or any type of parameter to which we are actually stored in the database. And that includes also the formation energy or the mixing entropy. Yes. And why is it good for us? It's good because we can use transfer learning. It's a very, for us, it was a good surprise, but that gives us really the new hope, and that's the reason why we are keeping this CGCNN model in our database. Very important message, which I want to emphasize here, is that we are not taking any foundation models and fine-tuning, but we train our own model with the help of materials project. And why we are doing that, so I explain it here. That's the so we at the very beginning, what we did is we took only material project data. We downloaded 8,000 label data and trained the CGCNN neural network or model for our DFT calculation. So we took B1, B3, B4 structures, total energy, bulk modulus, sphere modulus was actually taken as a label. And we trained the CGCNN network on material project. So you should understand that this is only compounds what we have trained on. And then we checked what is happening on our DFT data, which is on alloys. And what you see here for the bulk modulus and also for the sphere modulus, you see the beautiful correlation. So that's showing the training, and that's showing actually what is going on with our alloys. So that gave us the green sign to use the CGCNN or this methodology as a built-in network in our HADB, because it's an easy to develop, easy to advance type of CGCNN neural network. Unfortunately, the source-trained model was less good performing for the CIJ. So if we wanted to calculate the elastic constant or predict elastic constant, that was not so good. But what we did, we retrained that model. So since we had more and more data in HADB, so we added some certain part, fine-tuning our CGCNN model, and then you see here the results. The figure shows the blue ones are showing the distribution or the error. Yeah, I mean, okay, that's the bulk modulus deviation from the DSP value with our first starting CGCNN model, which was trained on the compound and the materials process data. And then the green one shows that we have actually included certain amount of new alloy data and then correlating with the rest. So the validated against the rest of the alloy data, you see the error has been reduced significantly. So that helps us just keep going and learn and add more and more data to the database. Yeah. So what we do then is that, of course, we wanted to test what happens if with the bulk modulus if you take any nitride for the periodic table. And this is the heat map what you actually can generate. What you see here is the coloring of the bulk modulus, and we color only the maximum one. So this is the coloring scheme, and we take the maximum one. That's what we are showing here. So, for example, if you would like to take a titanium-based alloy, so then you go here, and then you will see immediately that the titanium, zirconium, titanium, hafnium, vanadium, niobium, this part is an industry relevant materials are not all very actually have very high bulk modulus. Similar figures we have achieved for the fear modulus, and similar figures we can generate for the CIJ component. It's included. We can come to the other point where the ML or the inbuilt CGCNN or neural network works for industry. And this is the case where we are using some multi-component alloy, which is not at all in the database. I should say that at the moment we have binary and couple of ternary alloys in the database. But these ones, if I type in titanium, aluminum, vanadium nitride with this certain concentration, it's not there, not in the database. But the CGCNN models, based on the success of the transfer learning approach, can be used. And we did it. So that actually works very nice. So here on the right-hand side, you see the validation. Here, the y-axis shows the predicted value. Meanwhile, the DSP calculated value you will see on the horizontal. So you see a beautiful correlation. And now our new retrained machine learning predictor is actually working for all of these elastic constants. So which makes that happen. Okay, leaving the story of elasticity, we go to another point, which is more towards the nuclear industry, together with Westinghouse, where we are looking for materials which has very nice corrosion behavior. Since all these claddings which are holding the fuel rods or pellets, these uranium oxide pellets, so they are sitting in water. And here in this slide, I just explain what is the Kobe diagram to investigate bulk corrosion. So a little info about electrochemistry. So you have two sides of the electrochemical reaction, so the oxidation and the reduction side. And based on the boundary conditions of the hydrogen concentration or the electropotential, so you can build a phase diagram which shows which phases, which oxide phase or which ionic phase or which ions are stable at a certain concentration. So pH 7 is where we have a normal situation, so that's where people should look. And the question comes, how can we get this information if we have such a database? Yes, we can get it if we put together all the free energies. So if we put together the free energies of the reduction side and the oxidation side, then we can actually find the stable phase at the condition. So for that, what you need is just the free energy of the product, which can occur in the on the oxidation on the oxidation side. Sure. For that, of course, we cannot calculate everything. We have no tabulated data for all the ions. We don't know the activation energies of the ions, but we know the free energy of the incoming alloy, because that's what we can calculate, or we can use our machine learned models to predict at a certain concentration the formation energy or the mixing energy. But these are the more the relevant information. The ionic activation energies and all the energies for these ions are tabulated in materials project. And with the help and support with Christian Persson from materials project, we are building the HADB diagram. So here you can see an example that we took our collaborators this to know what is chromium niobium nitride, how it will perform at 300 degrees, it's 300 degrees C. No, it's 300 Kelvin. Sorry, yes. And then a different concentration. So you see the different concentrations, the calculated HADB diagram will occur here, it's shown here. With that concentration, so if you take pH, normal pH, water pH, which is this which also at nuclear reactors to keep the pH close to neutral, so around 7. So you will see that the stable phase will be here. That will be the alloy, and then there will be also the alloy, corresponding alloy, what you actually use. And also there will be some penta hydroxide compound in a solid solution. If you increase the niobium content, so then you will get this situation, which is the same. Again, the alloy will be stable, plus there will be around some solution with this particular pentahydroxide. If you further increase the niobium content, so to go to 50-50, then you will see that the chromium niobium alloy will be stable at that particular setup where you have no electrode potential, and then pH at 7. So that we call the immunity region, where the coating will stay as it is. If you further go with higher niobium content, then you will see again in this range where the chromia and the alloy will be coexisting. That suggests that with this concentration, if you set up if you deposit such a coating on a fuel rod, then you expect the standard oxide rate, oxide of the chromia plus chrome niobium, the alloy. So it will be passivated in a way that an oxide will passivate the corrosion of the material. And then, of course, I mean, if you use our CGCNN model, which is inbuilt, so you can actually calculate the HADB diagram for arbitrary alloy. Yeah. And then finally, I would like to also show one ongoing consideration, which is going towards the multi-scale situation. It's again a collaboration, collaborative work with hard coating industry and also with the nuclear industry. Here we go for the phase field simulation, where we would like to use the thermodynamic information to evolve the mesoscopic phase of the material. So we are no more atomistic, but all the atomistic informations are hidden here in the free energy functional, and that functional is known by HADB, either by the CGCNN model which we have. And then what we are looking for is the solution of these so-called Cahn-Hilliard equation. It's a fluid dynamic type of equation. So we are developing a machine and surrogate to approximate this solution, approximate the solution or speed up the solution to see how the microstructure is evolving in time. This idea will be solved not only this is true that the industry will see more the age hardening phenomena, or we'll see how the microstructure will affect the fuel cladding and the fuel design for nuclear reactors. But we have also the possibility to see and engineer later on some kind of metamateria where we have a particular microstructure with some interesting phenomena. Yes, I think with that I can close and say that yes, I went through the HADB. I showed our vision, how we would like to stack together the different layers, how we would like to work with industry, and how our easy machine learning model serving us and also industry who are using this database. So in summary, I would say with the help of HADB, we are heading towards the multi-scale and type of multi-physics modeling. So thank you very much. And now I'm open for questions.